Okay, so this thing is now recording and it just changed the picture. I don't know why it does that. And it's not focused very well. Well, I wish we had the ability to fix the focus in this camera. Showed a pretty picture that wakes up. I'm not sure that's a pretty picture. Not sure what it's even doing here, but there it is. Okay. So, oh, come on. Okay. Okay. So again, if your values of A and D were 12, 14, which they probably weren't, because A's never that big, and C and F were 42 and 34, then these would be your points. So it doesn't really matter what the numbers are. But of course, C is bigger than A, F is bigger than D. C is bigger than A, so this points to the right of this one. D is bigger. F is bigger than D, so this point's higher than this one. Could have been different. Next time probably will. Okay. Well, what we're asked is the average rate of change between X equals A and I said X equals B. Should have been X equals C. So get something B. That's great. Okay. Figured out how to do it for B. That's good. If not, that allows you a whole lot. Okay. It's only a daily quiz. It's not a big deal anyhow. So the average rate of change is what? Change in Y divided by change in X, right? So that's one. Right, that is delta Y over delta X. Now your open math gives you a formula. Okay. And I'm not even sure right now what the formula is and the thing you looked at. I don't really want you to think in terms of a formula, but the formula helps you check to make sure you're thinking right. Okay, so you should know the formula, but the idea is the idea. The change in this divided by the change in this. Okay. Now, what's the change in Y and what's the change in X? What I'd like to see you do, because you'll remember it better and it'll work better for you than just remembering symbols and stuff. It's a picture. Okay. First of all, I can take a straight line from this point to this point. Then I complete a right triangle with the sides parallel to the coordinate axis. The side parallel to the x-axis, the side parallel to the y-axis. We call this the change in x. Is 34 minus 14. In other words, the x value is 34 minus 12. It's not 34 minus. It's 42 minus 12. I could tell I did something wrong because you looked at me like I was crazy. Okay. It's 42 minus 12, which is 30. Now we can see that if I project down to this point and this point, we see that the x coordinate here is clearly 12. And the x coordinate here is 42. And if I go from this point to this point, the displacement is, give myself a lot of room there. The displacement here to here is I wrote that really small, but I just wrote 42 minus 12 equals 30. That's from here to here. So if you're in the interstate, you're at milepost 12, and then you go to milepost 42, you went 30 miles, right? Okay. Okay, so up here we have delta y. That's 34 minus 14, which is 20. Of course, I could do something over here. Here's 14. Here's 34. And from here up to here is 34 minus 14 equals 20. So you want to understand every bit of that. And if you don't totally understand it and find that you aren't applying it, you can come back to the beginning of the video for this class and read my, I'm not going to say words of wisdom, my attempt to help you understand, okay? I want to pursue wisdom. Okay, so anyhow, average rate is delta y over delta x. In this case, that's 20 over 30. Of course, that reduces to 2/3. And this is really important, so give you a minute to digest all that. But also make yourself note to make sure you understand the details of what I just told you. And the picture on the graph that corresponds to this calculation of the average rate of change. Okay, you're probably familiar with the idea of slope. Now, turn the camera off here, or the recording off for a second. And I'm going to ask you to tell me what two words come to mind if you think of slope. Okay, very good. I got a very quick answer, correct? And, okay, what's the rise here? Don't say because the recording time. But the rise in my case is 20 and the run is 30, right? So I'm just going to make a little note. We haven't really talked that much about slope. I'm not sure you open math assignment did. Okay. But the rise is right here. It might help. But this is the run. This is the rise. I'm going to write out a statement for the average rate of change of f of x with respect to x on the interval (12 to 42). Is equal to the average slope of the graph. Okay. I'm also going to give you a bit of terminology. I'm going to call this the fundamental triangle. And a bit of notation. Be good if you remember from now, but I'll tell you more about it when we study equations of straight lines and so forth. Okay, I'm going to put slope, which is 2/3, in a box right here. So when I look at this, I know that I've calculated the slope, and if my calculation's correct, it's 2/3. That's the average rate of change of F with respect to X on the interval 1242. Okay. So this whole picture should go with any calculation of average rate of change. All this thing in purple, all the labeling and everything, fundamental triangle for this interval and this function. This gives you a way to better visualize and understand rate of change. And as I've said, many of you, most of you, probably have at least an applied calculus course in your future. Okay, and this is average rate of change is the most fundamental concept you need to understand first semester of applied calculus. Okay. You can learn to do the operations and manipulate the symbols without understanding a bit of it. And that's what most calculus students do. But you won't have what you need to really understand it and apply it to whatever your curriculum happens to be. Okay, well, we just got a question. Is it the average slope or is it the slope? It's the average slope. And I'll explain why. And I'll explain in terms of this picture, okay? This picture's already cluttered up enough. Now, if we look here, so if we draw a straight line here, that's the average slope between this point and this point. Now, what's the slope of this graph? At this point, or what would be the slope of this graph if I had a very, what if I did the average slope between 2 points very, very close together near this one? Okay. Well, the average slope would be just the slope of a tangent. Okay, might be about like this. So that slope might even be 0. Okay. The important thing is what has a greater slope, this or this? How many think this has a greater slope? Raise your hand. I think it's a greater slope. Okay, how many think this has a greater slope? How many aren't sure? Okay, you don't have an opinion and you aren't sure that you aren't sure. Okay, well. Calculate the rise over run of one a triangle here. It's going to have practically no rise. It might be 0. Okay, but the run along this line, the run's whatever you want. Depends on how long you want to make the line. So does the rise. Okay, but it's very clear that the rise is a whole lot less than the run. The rise might even be a little bit negative there, the way I drew it. Tend to make it negative. Okay, well, I'm going to change colors here. This color is good and literally more. Okay, what do you think about the slope here? Well, by tangent line, I mean a line that touches the curve at this point, but doesn't go through the curve. Okay, and I can do that with a straight edge of the graph. So straight. We can lay that across the graph so that if I move it up to the graph, you adjust the slope just a little bit. It touches the graph right at this point. It doesn't go through the graph. It's called a tangent line. And it's about in that direction. Okay. Now, the slope of this line is greater than the slope of this line. It's steeper. Okay, slope is sort of a measure of steepness, but of course it could be negative. If it's going down, you have a negative slope. If it's going up, you have a positive slope. So you can be real steep going down, you can be real steep going up. So you got to be a little careful about using the idea of steepness. But it's clear that in this case, this is steeper than this, and they're both up. So this slope is greater than this one. Okay. Now, if I average these two slopes, they might come out kind of close to this one. Okay. And if I drew a million slopes at a million points along this curve and average those slopes, I should get something that's pretty close to that, real close to this average slope. Okay. Now there's some technicalities about that, and we just don't need to worry about it this time. Okay. But the idea, the concept, if you average all these slopes, you should come out with the average slope. Technicality is it average slopes at equal x intervals. Okay, all your points would be have the same run between points. Then you kind of average all the rises and should come out consistent with this slope. Okay, don't want to say too much more about that. That's more than I intended, but that's quite central to what we're doing in this course. I'm trying to prepare you for calculus, and that's what I'm talking about, is something you learn a little better in calculus, and you learn to use it, and you learn to think in terms of this thing. Okay, so my point is the idea of the average slope is very central to your ability to apply calculus, or to apply mathematics, or even to apply pre-calculus. Okay, pre-calculus stands on its own as an important course. And why are we teaching you this? It's not so you can do fancy algebra, although you have to do some fancy algebra. Don't get too fancy. Okay, you have to do some fancy algebra and incorporate these, and to be able to get the numbers that correspond to the things you really need to understand. But the point of this is not algebra. Okay, you lose forest for the trees if you just look at the symbols. Point is, big point of this course. There are a few of them, but the first one is average rate of change, and the idea of a rate of change and how it's applied. Okay, again, I said it, and I'll say it. I'm pretty happy with just the fact that it looks like everybody pretty much knew how to do an average rate of change. Because really the quiz is just there to, first of all, motivate you to get the homework done. Because you know when you come in here, you're going to have questions that are related to the homework. Okay. But second, so I can assess how you're doing, so I know what to say and know how much to say. All right, and I'm happy. Just got the rate of change and nothing else. I'm even happier if you got more than that. It looks like most of it there. Okay, so the next question is, what's f of whatever letters I put down there? I kind of screwed it up. You missed that point. Let's pretend I did it. Let's pretend that's our actual graph. Doesn't look all that much like this one. Everybody had a different graph anyway. Okay. And let's say again that here's 12. Here's 42. Here's 14. And here's 34. Okay. Now let's see, we asked for Actually, I did ask you for F at this point. Choosing one question with the other. Okay. So what's F12? Well, F12 is the coordinate of the point on the graph, y coordinate of the point on the graph, because y equals F. Y coordinate of the point on the graph directly above x equals 12. And we can see from the picture in these projection lines that that's 14. Okay. So also F of 42 equals 34. Okay. So now let's say I want you to estimate F of 20. How are we going to do that? Well, halfway between 12 and 42 would be 54 divided by 2, which is 27, right? So just one way I can do that. So, okay, well, average these two numbers, I get 27, and that's halfway between. Or you can do this any way you want. You could subdivide 42. Okay. You can put some kind of a scale in this graph. I don't really care where you put 20 in this case, but I want to see, how to estimate the value. So I'm just going to put 27 there. So I'm going to say 20 is right about here. It's a little simple left of halfway. And I'll be happier if you got it in a pretty good position. If this is just closer to the 12 than the 42, then I'm not unhappy with that. Don't expect miracles of accuracy. Later I will. But if we come up to the graph, well, F of 20 is the y coordinate that corresponds to x coordinate 20. And right there it is. Everybody? Okay. Not sure I saw projection lines in everybody's papers. I took a look. But this is y equals F of 20. And then graph point for x equals 20 is about 20. And if I come up to here, okay, halfway between 14 and 34 is 24. So 24 would be halfway. This is a little closer to 14. So I'm going to say, well, maybe about 20, 22. I use wavy equal signs for approximately equal to 22. Okay. Meaning that's an estimate. It's not exact. We don't know the exact result because there's no formula for the function. You just have the graph and you do the best you can. Okay, then. Solve the equation f of x equals 18. 14's here and 34 is here. 18 is a lot closer to 14 than it is to 34. If this is really 22, then 18 would actually be halfway between 14 and 22. So here's 18. That's where y equals 18. That's where f of x equals 18. I'm going to y equals 18 everywhere on this horizontal line that I. Now, what's the graph point? Graph point for y equals 18 is here. And we can project it down here. So this is 12 and this is 20. Halfway between 12 and 20 is 16. I'm going to say it looks like maybe about 17, might even be 18. Okay, so I can say that the graph point graph point's approximately 17, 18. So if I was grading this very strictly, you know, I at this point just be happy to see these projection lines and understand that you know that f of x is 18 and x is 17, or whatever estimates you make of these points. Okay. That's a picture of a solution of this equation. Okay. So okay, that's that of it. F of x is approximately 18. X equals, and x is approximately 17. And well, now we can say, and think about this, that f of 17 is approximately 18. And you want to digest that for a minute. Okay, so it's important to understand this statement and all these statements. So you want to review because they'll help you understand, number one, how to read a little bit of mathematics rather than just do it by what it looks like. Okay. So f of 17 is approximately 18. So x equals 17 satisfies the equation f of x equals 18 because when you plug x into the equation, you get true, or approximately true statement. It satisfies it as best we can using an estimate. And that's a lot easier to understand than all the operations you've got to go through to solve various kinds of equations. And if you have this picture when you're solving equations, you always know what you're doing. You always have a perspective on what everything means. And that helps you kind of focus on what's going on in the course. Okay, how do you solve a quadratic equation? How do you solve a linear equation? How do you solve an exponential or a logarithmic equation? These equations are not that hard to solve. I mean, they can get really hard. Give you a polynomial equation that nobody can solve. Almost any polynomial equation nobody can solve. Okay, you can put it that way. You can't get an exact solution. But if you have the graphical picture, it gives you a lot of information where you can do important approximations. Okay. I'm noticing too much about that one now either, because we'll understand it when we get to it. Okay, so there we have it. Okay, again, I apologize, I lost track of the camera. But to solve f of x equals 18, well, we did what we did here. Okay, f of x is 18. F of x is 18, y equals 18, y equals f of x, y equals 18 everywhere in this line. So if we take the point where this line intersects this graph, we can project downward and find the value of x that makes f of x 17, because this means that the graph point for f of x equals 18 is this, and its coordinates are 17, 18, approximate coordinates. So f of x is approximately 18. So f of x is approximately 18 when x is approximately 17. This means that f of 17 is 18. Thus, x equals 17 satisfies the equation f of x equals 18. It's a solution. So I say, okay. Now, another thing we learned to do in the course. Get mixed up between the classes, so let me double check what I'm about to say. The problem with this calendar doesn't show me what went before, but yeah. You did the assignment in the basic parent and toolkit functions. So you're learning how to construct graphs. So you are learning what to look at and how to look at graphs. So if I ask you to construct the graph of the basic exponential function and solve the equation 2 to the x equals 3, you don't know how to do that yet. You won't know until sometime in late October, early November. Unless you look ahead or unless you've already seen it, okay? And usually people that come into this course, it's really not part of the prerequisite courses. So unless you've had something like a pre-calculus or analysis course previously, you wouldn't know. Not hard. There are a couple of rules. By the time we get through polynomials and rational functions, these rules will seem like a relief. Okay, because those things are fairly challenging, but not so much if you know about the basic toolkit parent functions. Okay, so right now you know one way of solving 2 to the x equals 3. You do a good graph of 2 to the x. You find y equals 3, you come over here and you can get off your x value. That's your solution. And then you plug that back in and then go to the calculator, punch it in, and you find out, yeah, you were pretty close. Or, boy, you really screwed that up. You better go back and draw it again. Okay, does that make sense? But you're developing the first skills in graphing and constructing graphs rather than punching them into a calculator without ever thinking about what they mean or why they have the shape they do. And sometimes you got to do that. I mean, some functions are so damn complicated. I can't do it. Nobody can. Okay. But for the basic functions, the pictures are simple. So now I want to talk about composite functions. There are two ways of building functions in this course. One is by composite functions, the other is by transformations. So we're going to talk about composite functions today. First, we're going to talk about transformations. Okay. Now, transformations actually in many ways simpler in terms of what happens to the graph. It's like the transformation. I'll tell you what the transformations are. The three main ones, and there's a fourth one that we use sometimes. You stretch the graph out in this direction. Okay. So just imagine it's on a piece of stretchy paper and you stretch it out this way. Okay, that's a transformation. And that has a corresponding algebraic form. Very simple. And if the functions, for the basic functions, it's always really simple. Okay, another thing is you can just raise the whole graph up. So if the x-axis is here, okay, you raise the thing and the graph is like here, you just raise the graph up, raise every point up by the same amount. So the graph retains its shape, it's just higher or lower. You could raise it down. That makes sense. You can lower it or raise it. Okay, it's called a vertical shift. Or you can move it to the right or left. And once you can do that, you can do just a whole lot, just with the basic functions, because most of the functions are built by transformations and composites of basic functions. Now, composites, if you understand function notation, and I didn't really test you on that today, but you did well on this. So I think you're well prepared to understand the function notation. If you write down each of these, you don't need to do that on scrap paper, you do it in your notebook. Okay, what's f of 3? Well, if I write f of 3, I've replaced x by 3, haven't I? So it's pretty simple. If I replace x by 3, I've got to replace this x by 3. And of course, you can calculate that. It's equal to 8. I'm not even going to bother. I just want to see that you're substitute. Okay. Now, what about f of x plus h? Well, x here has been replaced by x plus h. So wherever I see an x in this whole definition, I've got to replace it by x plus h. Well, where do I see an x? I see it here. So that's going to be 2 to the x plus h. Each of these is exactly like this, except with a different expression inside the parentheses. So then what's f of g of x? Well, x is being replaced by g of x, so that's 2 g of x. Okay. Some of you got all these. Some of you, had a little bit of a problem. Make sure you really understand. But I think I told you last time, and what helps you get through the math assignment, function notation. Okay, because everybody did pretty well. Everybody here did pretty well. There's a couple people that aren't here. One. Apparently the rain caused some trees to fall on his power lines. Okay, and emailed me this morning. Okay, so anyway, there we are. Okay, well, let's now do a composite function. This is actually the composite of f g of x. So f circle g of x is defined to be, that says DEF down there. This is the definition. This is f of g of x. Okay. You wonder why we have f circle g, because sometimes we want to talk about the function f circle g or the function f plus g, and we want to write it with a circle rather than this, and you'll see how that works. Okay. Then there shouldn't be anything confusing about it, and except why we bother? Why don't we just write this? Okay, you'll see a reason for that. Okay. And we've got 5 minutes to get this one example done. It's going to be good. I'm going to give you a minute to see if you can write that out. Don't bother writing out the question. Just write out what you think f circle g of x would be and put a circle around it. Is it one short time? Okay, people are having a little bit of trouble with this, but let's go back to what we've done. We've figured out that f of g of x has to be 2 to the g of x, right? So we can start with the definition. F circle g of x is defined to be f of g of x. So this is always true. Okay. Now, this f of x didn't really have a whole lot of trouble with the idea that f of g of x is 2 to the g of x, right? So most of you are pretty much right here, and I think everybody will be if you think about it a little bit. Now that's 2 to the g of x, but what's g of x? G of x is x squared. So we just write 2 the x squared. Okay. Now I could have let g of x equal negative x squared, in which case we'd have 2 to the negative x squared. Graph of this function. Here's a well-known bell-shaped curve. It's actually a transformation of the bell-shaped curve, okay, that we use in statistics. But there it is. Now, real quick, see if you can do this. What could you write out for g of f of x? See if you can write this out quickly. Since we're actually out of time, I'm going to give just a short time, then I'll write it out for you. I'm not going to look at what you did, but I wanted you to think about it for a minute. Okay, so g of f of x, well, g of x is x squared, right? So G of f of x, we replace x by f of x, we get G. Sorry. Not sure what I said there, but I think it was right. We replace x by f of x. If we replace x by f of x, then this x has to be replaced by f of x. So it's f of x squared. And of course, that equals 2 to the x squared, because f of x is 2 to the x. Okay. Now, one of your assignments for next time, and it's a review of something you're supposed to know. Some haven't talked about it because the exercise will straighten you out or review that for you. Okay. It's just the rules for exponents. The rules for exponents tell us that this is 2 to the 2x. Okay. And 2 to the 2x. 2 squared to the x. This is 4 to the x. Now you're probably a little bit rusty in the rules for exponents.
Sorry, I didn't realize you had another one.
Okay. It's fine. You can always walk in. Just walk in front of the camera and you did. Okay. It's great to have. So again, you're probably a little rusty in the rules for exponents, but hopefully you'll understand this by the time you've done that. It's a pretty easy assignment if you've done the rules for exponents. Okay. And then you have an assignment for composites that'll be due next time. So we get to talk about transformations.